Hi everybody, today's note is about the factored form of a polynomial equation. So before we get into polynomials, let's remind ourselves about the factored form of a quadratic and what it helps us do. So there's three different forms of a quadratic function. Same thing with polynomials, there's lots of different forms. And the factored form, so let's say we have f of x equals x minus 2 and by x plus 3. Okay, this gives us a quadratic function. We know it's quadratic because when we expand, x times x would be x squared, so the function has a degree of 2. We are also able to see the zeros or the x-intercepts because if we set f at x equal to 0, then either x minus 2 would have to be 0 or x would be 2 because 2 minus 2 is 0. So that means 2, 0 is a coordinate on the quadratic. And x plus 3 gives us a 0 of negative 3 because to make this thing 0, to make this binomial 0, you would need a negative 3 plus 3 to get 0, and that would make this whole thing 0, giving a y value of 0. So you get the point negative 3, 0 as one of the coordinates. Okay, so the whole point here is that if you keep adding, zeros, okay, you can see what happens. Okay, so if I have, I don't know why it's not letting me do this. Okay, so if I have f at x equals, so let's say I still have x minus 2 and x plus 3. What if I add now an x minus 5? What's going to happen? Well, now it's turned into a cubic because we would have an x times an x times an x, which gives us a cubic. And we still have the zeros of 2 and negative 3, but we have another 0 here at positive 5. So if you were to zoom out, you can see that this looks like a cubic. Okay, the degree is 3. The leading coefficient is positive because when you multiply all these by each other, it would just be x positive x cubed. So that explains the end behavior doing what it does. And you have the zeros there at 2, negative 3, and 5. So the whole point of this is that when you are given a polynomial in a factored form, you have enough information to answer questions about it and to make a pretty decent graph of what it looks like. So that's what we're doing today. So our learning goals: make connections between a polynomial function in factored form and the x-intercepts. Then sketch the graph of a polynomial given its factored form and using other key features that you know about it, like the degree and the leading coefficient. Determine an equation of a polynomial if you're given a set of conditions or if you're given the graph of that, and determine the equation of a family of polynomial functions with a given set of zeros and of the member of the family that passes through another given point. So if I tell you that a polynomial has zeros 5, 2, and negative 3, there are an infinite number of polynomials that could go through those 3 points, just depending on how steep it is in between those and what happens other than those zeros. But only one specific polynomial will exist if I give you even one other coordinate that's on that polynomial. Just knowing one other coordinate besides the zeros is enough information to make a unique polynomial. So the family of polynomials that go through those coordinates, the x-intercepts, there's infinite, but once you get that other piece of information, you're able to specify which family member that is. Okay, so recall that the zeros or the roots of a function are all values of x where f at x is equal to 0. So the y value is 0. That's what it means to be on the x-axis. So the factored form of an equation is of this form, okay? So, notice here, don't forget about this a value, okay? There's some a value out front, and if there is no a value out front, then that just means a equals 1, okay? So P1, P2, P3, and then all the way up to Pn, those are the zeros, okay? So again, to determine the number of the zeros, we set y equal to 0 and find all the possible x values for which this is true. This is achieved by setting each factor equal to 0. So The first factor is x minus p1. We set it equal to 0. So then x is equal to p1. Okay? If you have some value in front of x, like ax minus p1 within the factor, then your x would be p1 over a. All right, so that's how you solve for the 0. Note that the degree of the function in factored form can be determined by multiplying x values. So here we would have an x times an x times an x, so that would be cubic. Now careful here. Here you have 2 x's and 3 x's, so that would be quintic, which means degree of 5. Okay, so because it's 2 and then 3. So here's a new definition, the order. The order is the exponent to which each factor is raised. So x minus 3 is a factor. Oops, x minus 3. And its order is 2. X minus 1 as a factor has an order of 1. So if you're looking for the degree of the whole function, you just add up the orders if it's in factored form. The order is just looking at each factor individually. So each factor gives us a root. The order of each factor determines what the function looks like at this root. Okay, and please just recall that root is another word for x-intercept. Okay, so each factor will give us an x-intercept, and then the order of that factor, so whether it's all raised to the power 1, to the power 2, or to the power 3, will tell us what the function looks like at that root. So you might be kind of confused, but you'll see. The most obvious one is linear. So let's imagine we have a function like f of x equals x plus 2, x minus 1, and x minus 4. So notice here, first of all, that our a value is positive. Therefore, we know the end behavior. Okay, so that means, remember, that's kind of like linear. So it starts down here and it's going to end up there. That's the general end behavior, right? And we know that it's cubic. Okay, because x times x times x is cubic. Okay, so we can determine here that the zeros are at -2. So if we go boop, 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 real official, eh? Okay, so we have a 0 at -2, at 1, and at 4. Okay, we know that the curve will start down here, okay, and end going up. So we have to estimate what happens in the middle here. So notice that they all have an order of 1. So you can draw little imaginary ones if you want there, but all of these zeros have an order of 1. So that means that the corresponding x-intercept is a point where the curve passes through the x-axis. So I just go right through here. It's going to do something here, I don't know. Okay, there we go. So that's an estimation of this curve. Now, if we were to zoom in on one of these zeros, it would look like just a straight line right at that point. It would look linear because it's going right through. So it just looks like a straight line. And that matches with the order of 1. Now, if something has an order of 2, however, it's going to look quadratic at that point. So let's give another example here. Let's do y equals 1/10. These are real functions. I didn't just make them up on the spot. X plus 3 to the power 2, and then x minus 2. So this is another cubic function. Note that it's cubic. And note that a is greater than 0. So the end behavior will start down there and it'll end up there. Okay, and if we put our zeros, 1, 2, 3, 4, 1, 2, 3, 4, really official. We have a 0 at -3 and a 0 at 2. So this -3, 0 has an order of 2 because its bracket here is raised to the power 2. and this x-intercept has an order of 1. So we're going to start from down here, right, and end up here. But what happens in between? Well, because this has an order of 2, it's not going to actually go all the way through this 0 to the other side. Okay, that's what we're used to seeing. But if it has an order of 2, this 0 is actually a turning point, and the x-axis is a tangent. So it actually goes up to the 0, touches it, and then turns back down. Okay, and then this guy is just a linear one, order of 1, so it just goes straight through. Okay, and continues on. It probably, you know what, it wouldn't look that, it wouldn't look quite that straight up. It would be more like, you know, growing gradually like that. So if you were to zoom in on the graph right here, it looks kind of like a quadratic at that 0, and that's because it's raised to the power of 2. Okay, and that means that the x-axis is then tangent to the curve at that point. Okay, now you can guess what happens if the order is 3, it's going to look cubic. So if we have the function y equals 1/5 x plus 1 cubed x minus 1, okay, notice that this is a quartic function with a positive leading coefficient, so it's going to start going up and it's going to end going up. Okay, so if we make do, okay. Our zeros are going to be at -1 and +1, and we're going to start from up here and end going up here. But what happens in between? Well, this 0 has an order of 1, so it's just going to go straight through and look linear. But this x-intercept has an order of 3, so it's going to look cubic. It's going to look cubic at that point. So this one's really hard to draw, and I don't even know how I'm going to do it on this trackpad, but you have to kind of like bring it down and go, and then start going the other direction. Okay, and then it goes straight through. So it still goes to the other side, but it should look like the x-axis is tangent. So let me try that another one again. And I can do this in person in class. Okay, so it should get close, start curving, and then go down like that. Okay, something like that. So if you got in really close, it should look like a cubic where they have that little curve at that point. That's the idea. Okay, so order 1, linear, order 2, quadratic, order 3, cubic. All right, so when you sketch graphs, you're going to be given a function like this, so you can determine what the zeros are. You also need to look at the leading coefficient and the degree of the function to know the end behavior, and then look at the order of each factor to tell me what the 0 looks like at the 0. So you hopefully recognize here that this is there's an x, so 1, 2, and then 3, 4, right? That's 2 x's there. So this is a quartic because there's 4 x's, and it opens up. Quartic. That opens up, sorry, not up, down. Since its a value is 0, or sorry, negative. Right? The zeros are going to be -2, 0, 1, 0, and 3, 0. Okay? Now, it's always useful to find the y-intercept as well. So to find the y-intercept, you just find f at 0, put 0 into the function, bloop, 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 you get 18 in this case. Okay, so with this information now, I'm going to sketch as close of a curve that I can. So my x values are going to increase by 1. So I'm just going to label 2 and -2 there so you know that. But my y values are going to increase by 5s. 5, 10, 15, 20. So we'll just put a 10 and a 20. Okay, So plot your zeros first. So we have -2, 1, and 3. Okay, and it opens down, so we're going to be starting from down here and ending going down. Okay, I know I have a y-intercept at 0, 18, so I can label that as well. And so if I want to get like a better understanding of what this looks like, I can test values on either side of -2, on either side of 1, on either side of 3. But really knowing the end behavior and everything is enough information. So you just go up, okay, because this one has a degree of 1. You make sure you go through your 0. Now this x-intercept also has a degree of 1. And now this x-intercept has a degree of 2. So you touch it and then you go back down. Okay, so it looks quadratic at that point. Now think about it. If you had gone straight through there, then it couldn't have been a quartic because it would have had the wrong end behavior for a quartic. And there's no other x-intercept that would have allowed it to go back down again. So one of these guys at least had to have this end behavior in order for that to be a quartic. So there you go. And you want to label the zeros, okay, to be thorough. Okay, if you want more accuracy, or if the question requires more accuracy, you can test values on either side of zeros. So for example, you could test x equals -3 and x equals -1. Like what I mean is just put them in the function and see what y values you get and plot those as well. Okay, here's example 2. Now we're able to factor this because it has a common factor. So we can factor this to, we can take out an x cubed and then we're left with just x plus 2. Okay, so that means that this graph, we know it's quartic. And this one opens up. And the zeros then, so this would be x equals 0 and x equals -2. Okay, the y-intercept is 0, 0. All right, so to graph this, again, we need our little points here. So this is going to be -1, -2, -3, 1, 2, 3. And I don't really do much on the y-axis, so that's all I'm going to label for now. So our zeros are at 0, 0 and at -2. Okay, now notice x equals 0 has an order of 3 and x is -2 has an order of 1. So we start from this because we know the end behavior, it opens up, so it has to look like this. But now we got to be really careful because we got to approach this guy. This is, I really don't love doing this, but we got to approach this guy like a cubic. Okay, and then it goes straight a little bit before it comes up again. And that should not look curvy like that. That should look more like, you know, like this. Okay, so you've got to find a way to make that look obviously cubic there, and then label the key points. And then label this as f of x. All right, so again, you can test values on either side to make it more accurate. So here's some practice for you. So I actually do want you to go ahead and practice this, and please actually remind me tomorrow. I want you guys to take this up in your groups. Okay, so this is part of the video to do this practice. I want to see that it's, well, if you get it done, you'll hopefully have more time in class tomorrow to actually work on stuff. So really try to consolidate these concepts by doing these sketches now. Okay, you can check them using GeoGebra to make sure you did it right. So just remember the first step in all of them is to determine what type of function. So is it cubic, quartic, quintic, what is it? What's the end behavior like? Okay, so does it go from here and end up here, or from here down here, or like this, or like this. What does it do in general? Then you find the zeros, and then you find the y-intercept, okay? Because that just gives you a more accurate view of what's going on. So that's what you need to do for all three of these. Okay. Finally, we get to creating equations. So this is when you're given the zeros or given a graph that shows the zeros, and you need to actually create an equation in factored form. Okay, so the first thing you got to do is substitute in the zeros, x1, x2, etc., into the general factored equation, noting the degree and order. So y equals a, x minus x1, and then you got to decide what the order is, okay? That's what's different. So if it looks linear, like it just goes straight through, then you just leave the order as 1. If it's a turning point, it looks quadratic, so it touches it and then goes back down, or touches it and then goes back up, then that should be a 2. And if it looks cubic, then that should be a 3. And then you keep doing that for however many zeros there are, all the way up to x minus xn. Okay, where we can put a question mark for the order. So this is the big thing that you got to remember. You got to actually figure out what the order is. Okay. Substitute the coordinates of an additional point and solve for a. Okay, so that's the other part that people forget, is that it's not enough to just put the zeros in. You got to substitute in something that's not an x-intercept and find what your a value is. And then write your equation. It can then be expanded if it doesn't want it in factored form. So here's an example. Notice that this looks like it could possibly be a quartic. It could be something to the power 6. But anyways, we notice here that we have our zeros are x equals -2 and x equals 3. So our function then is a bracket x plus 2. Okay, remember it's plus 2. And we'll say to the power 2 because it looks quadratic there. Okay, they're both the order 2. So this is an order 2 and this is an order 2. And x minus 3 to the order 2. So this makes sense because when you factor this out or expand this out, you would get x to the power 4, which matches what this looks like. Okay, now we're going to sub in our other known point, which is 2, 4, and solve for a. So 4 equals a, bracket 2 plus 2 squared, bracket 2 minus 3 squared. So you get 4 equals a, 16 times 1. So a is equal to 1/4. So f at x, I'm going to write under my head now, aren't I? Here, I'll write it over here. F at x equals 1/4, x plus 2 all squared, x minus 3 all squared. And you're done. Yay! If you want, you can put in the 0.2 and make sure you get 4 out of it to test it. Okay, here's another example. So we have the path of a dolphin. Okay, write the equation that represents the height of the dolphin over time. Okay, so hint, the first maximum height of 0.5 meters occurs after 3.5 seconds. So we can label this as 3.5, 0.5. Okay, so this is a situational problem. So we need to identify variables, don't you forget. So let t, actually we can use function notation. So it's height. So let h at t represent height of the dolphin above water, okay, because we can have negative here because that's below water. So the height above water, that's important that you add that. In meters, you got to have the units at t time in seconds. Or sorry, it's better to say at time t in seconds. So now you go ahead and do the exact same thing that we did above, just using these coordinates. So I would encourage you to pause the video and try it yourself. Okay, so you'd get an a value out front that we need to find later. So t minus 2, t minus 6, t minus 10, t minus 14. Okay, now we're going to put in the point 3.5, 0.5. You should get that your A value is negative 0.002. It makes sense that it's negative because it's opening down. And now you can write your function h at t equals, and then write this whole thing, negative 0.002, and then all the factors. All right, so that's the note for today. Thanks for watching. Hope you learned lots.